Look up at the night sky and you'll see a universe full of wonders, spiraling galaxies, glittering stars, and the faint glow of distant worlds. But hidden among these cosmic marvels are structures so strange, they defy everything we thought we knew about how galaxies form. Ring galaxies, those bizarre, donut-shaped whirlpools of stars, aren't just rare, they're cosmic anomalies, each one a puzzle begging to be solved. Picture a galaxy not as a familiar spiral or a chaotic blob, but as a perfect, luminous circle, as if someone took a celestial paintbrush and sketched a halo in the darkness. How does something like that even exist? The answer lies in a series of phenomena so strange, so utterly unexpected, they challenge our very understanding of the cosmos. Today we're diving into the heart of these enigmatic ring galaxies to uncover 30 of their most mind-bending secrets, from ghostly gaps where stars simply vanish to the violent collisions that twist entire galaxies into cosmic rings. These aren't just quirks of nature, they're clues to some of the universe's greatest mysteries. What happens when two galaxies collide in just the right way? Why do some of these rings flicker with bizarre, unexplained light? And could these strange structures hold the key to understanding dark matter itself? Each phenomenon we'll explore is a piece of a larger puzzle, one that astronomers are still scrambling to solve. This isn't just a tour of distant cosmic oddities, it's a journey into the unknown, where every discovery raises new questions. By the time we're done, you'll see the night sky differently, knowing that even the most seemingly serene galaxies harbor secrets that defy logic, so buckle up. We're about to venture into the depths of space to uncover 30 of the strangest, most awe-inspiring phenomena hidden within ring galaxies, and trust me, what we find will leave you questioning everything you thought you knew about the universe. Imagine a galaxy so strange, it looks like a cosmic bullseye, not one, but two perfect rings of stars spinning silently in the void. This isn't science fiction, it's the reality of double ring galaxies, one of the most baffling structures in the universe. Take Hoag's object, discovered in 1950 by astronomer Arthur Hoag. At first glance it seems impossible, a brilliant yellow core surrounded by a flawless blue ring, with a ghostly gap between them. But the real shock came when astronomers spotted a second, fainter ring lurking even farther out, turning this already peculiar galaxy into a celestial nesting doll. How could such a thing form? The leading theory points to violence, an ancient collision where a smaller galaxy punched straight through the heart of a larger one. Like a rock tossed into a pond, the impact sends ripples of stars outward, creating concentric rings that linger for billions of years. But here's the twist, some simulations show these double rings shouldn't last. The gravitational dance of stars should erase them over time, yet there they are, glowing defiantly. Could dark matter be the invisible hand holding these rings in place? Some researchers think so, suggesting its mysterious gravitational grip might act like cosmic glue, stabilizing the rings in ways ordinary matter can't. Then there's the odd case of galaxies like M6444741, where the rings aren't just stacked, they're warped, as if space itself twisted them. These contorted rings hint at something even stranger, multiple collisions or perhaps encounters with unseen dark matter halos, bending the galaxy's structure like a funhouse mirror. Every double ring galaxy tells a different story, and each one pushes astronomers to rethink the rules of galactic evolution. What's clear is this: in a universe where simplicity seems rare, these celestial oddities remind us that the cosmos loves a good mystery. At first glance, the empty gaps in ring galaxies seem like cosmic deserts, vast, starless expanses separating the brilliant outer ring from the galaxy's core. But look closer and you'll find something extraordinary. Stars are being born in these so-called voids. It defies logic. How can new stars ignite in regions that appear devoid of the gas and dust needed to create them? The answer lies in the aftermath of chaos, the shock waves and density waves rippling through these galaxies like cosmic tsunamis. Take the Cartwheel Galaxy, a sprawling ring over 150,000 light-years across. Its gap isn't truly empty, it's a breeding ground for stars thanks to a violent collision millions of years ago. When a smaller galaxy tore through its center, the impact sent shockwaves racing outward, compressing gas clouds in its wake. Like squeezing a handful of glitter, those sudden pressure spikes triggered star formation where none should exist. But here's the twist: the stars aren't forming randomly. They're aligning along invisible ripple patterns called density waves, the same forces that create the spirals in galaxies like our Milky Way. In ring galaxies, these waves act like celestial conveyor belts, dragging gas and dust into dense pockets that eventually ignite into stellar nurseries. What's even stranger is the timing. In most galaxies, star formation slows over billions of years as fuel runs out, but in the Cartwheel's gap, it's happening in bursts, like a strobe light flickering in slow motion. Astronomers suspect the initial collision set off a chain reaction, each new generation of stars heating the surrounding gas, preventing it from collapsing again until conditions cool enough for another round. This stop-and-start cycle creates eerie, isolated clusters of young stars floating in the void, their blue light a stark contrast to the older, yellower stars in the ring. Then there's the mystery of the missing material. Some of the gas in these gaps isn't forming stars at all, it's being pushed outward, cooling into invisible clouds too faint to detect. Could these hidden reservoirs fuel future star formation, or are they destined to drift away forever? Observations with telescopes like the James Webb Space Telescope are beginning to reveal answers, but every new discovery only deepens the puzzle. Ring galaxies don't just challenge our ideas about where stars can form, they're rewriting the rules entirely. And as we study these cosmic laboratories, one thing becomes clear: in the vastness of space, even emptiness can teem with life. Dark matter should behave predictably, clustering around galaxies in smooth, invisible halos that guide their evolution, but ring galaxies laugh at our expectations. Here, dark matter doesn't just lurk in the background, it twists itself into knots, defying every simulation astronomers throw at it. Take the case of UC 2944, a ring galaxy where gravitational lensing, a phenomenon where the galaxy's mass bends light from objects behind it, revealed something bizarre. The dark matter isn't evenly distributed like it is in most galaxies. Instead, it's clumped asymmetrically, concentrated in strange, lopsided pockets that warp the ring's very shape. Computer simulations predicted dark matter should settle into equilibrium, smoothing out over time, but when researchers compared these models to actual observations, the mismatch was staggering. The dark matter in ring galaxies seems to have a memory, preserving the chaos of ancient collisions. Imagine throwing a handful of marbles onto a trampoline. In a normal galaxy, they'd roll toward the center, settling into a predictable pattern, but in ring galaxies, the marbles freeze mid-motion, as if an unseen hand rearranged them into jagged, uneven piles. This isn't just a curiosity, it's a crisis for our understanding of how dark matter interacts with itself. Could some unknown force be at work, or are we missing a fundamental piece of physics? Then there's the case of the orphan dark matter in W28512, a ring galaxy where the invisible stuff appears completely detached from the stars. Observations show dark matter lingering far beyond the visible ring, like a ghostly echo of the galaxy's violent past. Some theories suggest it's evidence of a slingshot effect, where the collision that formed the ring hurled dark matter outward while leaving stars behind. Others propose darker possibilities, that we're seeing hints of exotic dark matter particles interacting in ways our models can't yet explain. Every new observation deepens the mystery. Telescopes like the Vera C. Rubin Observatory are now scanning these galaxies for subtle distortions in starlight, mapping dark matter's hidden architecture in unprecedented detail. What they find could rewrite the rules not just for ring galaxies, but for the entire cosmos, because if dark matter doesn't play by the rules here, where else is it breaking them? Most galaxies spin like serene cosmic pinwheels, their stars and dust swirling in a single flat plane, but then there's NGC 660, a galaxy that defies the rules, wearing its ring like a belt around its waist. This is the bizarre world of polar ring galaxies, where rings of stars, gas, and dust orbit at right angles to the main disk, as if some cosmic prankster tilted the universe 90 degrees. These structures aren't just rare, they're cosmic tightropes balancing in a delicate state that shouldn't last, yet here they are, challenging our understanding of how galaxies evolve. So how does a galaxy end up with a ring perpendicular to its disk? The leading theory involves a galactic heist, a larger galaxy stealing material from a smaller, doomed neighbor. Picture a dwarf galaxy venturing too close, its outer layers torn away by tidal forces. Instead of falling into the main disk, this stolen gas and dust gets slung into a polar orbit, settling into a ring that spins over the galaxy's poles like a halo. Over time, new stars ignite in this misaligned ring, creating the stunning, lopsided structures we see today. But there's a catch: these rings are unstable. Without constant reinforcement, they should warp, collapse, or merge with the main disk within a few 100 million years. The fact that we see them at all means they're either younger than we think, or something, perhaps dark matter, is propping them up. NGC 660 is the poster child for these oddities. Its polar ring isn't just a thin band, it's a sprawling, twisted loop of gas and young stars, strewn with pockets of intense star formation. Infrared observations reveal something even stranger. The ring is riddled with filaments of dust, some stretching thousands of light years, as if the galaxy is shedding material like a snake shedding skin. This suggests the ring isn't just a relic of a past collision, it's still actively evolving, with gas flowing between the ring and the main disk in a slow, cosmic dance. Then there's the mystery of the missing dwarfs. If polar rings form from cannibalized galaxies, where are the remnants of those galaxies? In many cases, there's no trace of a core or surviving stars from the victim, as if the larger galaxy swallowed it whole. Some astronomers propose an alternative. Perhaps these rings come from cosmic filaments, streams of gas funneled into the galaxy's poles during the early universe. Without clear evidence, the debate rages on. What's certain is this: polar ring galaxies are more than just curiosities. They're natural laboratories, revealing how galaxies interact, grow, and sometimes defy gravity's expectations. Every new observation peels back another layer, showing us just how wild and unpredictable the universe can be. Most galaxies follow a familiar recipe: a bright, dense core surrounded by swirling arms or a glowing disk. But some ring galaxies break the mold entirely, existing as hollow cosmic hoops with no central bulge to speak of. These eerie, coreless rings float in space like celestial donuts, and their very existence forces astronomers to reconsider how galaxies live, die, and sometimes vanish from the inside out. At the heart of this mystery lies NGC 644741, a galaxy so strange it looks like a portal to another dimension. From a distance, its perfect blue ring sparkles with newborn stars, but peer into its center and you'll find nothing. Just a ghostly void where a bustling core should be. One theory suggests this missing heart is the aftermath of a cosmic hit and run, a smaller galaxy plowing straight through NGC 644741 center at breakneck speed. The collision's force wouldn't just scatter stars, it could have ejected the entire core, flinging it into intergalactic space like a stone catapulted from a sling. Simulations show such violent encounters are possible, but they require near-perfect angles and speeds, making these coreless rings cosmic rarities. Yet there's another, even stranger possibility. What if the core didn't vanish, but faded? Some astronomers propose these galaxies might be the elderly survivors of a different evolutionary path. Over billions of years, their cores could have exhausted their gas, stopping new star formation while the outer ring, fed by fresh gas from intergalactic space, kept burning bright. Without young stars to light it up, the core would dim into near invisibility, leaving only the ring as a luminous farewell note. Then there's the wild card dark matter. If these galaxies formed in regions where dark matter was sparse or oddly distributed, their cores might never have fully condensed, leaving them structurally weak and prone to disruption. Observations of ENIO 644741's gravitational distortions hint at this, showing a lopsided dark matter halo that could have destabilized the core long ago. Whatever the truth, these hollow rings are more than cosmic oddities. They're stark reminders that galaxies don't always play by the rules, and that sometimes the most revealing secrets lie in what's missing. Some rings don't just curve, they twist, warp, and contort as if space itself were crumpling them like paper. These aren't flaws in cosmic design, they're gravitational graffiti, scars left by encounters with invisible forces. Take the Leo ring, a colossal loop of gas and stars drifting through space like a celestial hula hoop gone rogue. Most rings sit neatly around their galaxies, but this one. It's bent at odd angles, fragmented in places, as if some unseen hand tugged at its edges. The culprit, likely a close call with another galaxy, whose gravity stretched and distorted the ring like taffy. But here's where it gets weird. The Leo ring isn't just warped, it's too massive for its own good. This sprawling structure contains enough gas to build billions of stars, yet it's barely forming any. Conventional wisdom says such dense gas clouds should be stellar nurseries, bustling with newborn stars. Instead, the Leo ring lingers in eerie stillness, its gas too turbulent to collapse. Some astronomers think it's trapped in a gravitational tug-of-war, jostled by nearby galaxies. Its gas is constantly stirred, preventing the calm needed for star birth. Others propose darker forces. Could an invisible dark matter subhalo be pinching the ring, disrupting its structure from within? Then there's ESO 509-G026, a galaxy whose ring doesn't just bend, it spirals, looping around the core in a corkscrew of stars. This isn't the orderly spiral of a Milky Way, it's a cosmic tangle, as if the galaxy were caught mid-twist. Simulations suggest such extreme warps come from oblique collisions, where galaxies strike each other at odd angles, sending shockwaves that torque the ring into bizarre shapes. Yet even these models struggle to explain the persistence of these distortions. Over time, gravity should smooth out the kinks, unless something else is at play. That's the real puzzle. Warped rings aren't just accidents, they're snapshots of galactic violence frozen in time. Each distortion encodes a history of near misses, collisions, and gravitational whispers from the cosmos. And as we study them, we're forced to ask, do we really understand how galaxies interact, or are we just seeing the surface of a far stranger universe? Most galaxies light up with the glow of countless stars, but some rings defy that expectation, entirely floating through space as ghostly loops of pure gas, utterly starless. These cosmic enigmas, like the sprawling Leo ring, aren't just empty, they're overflowing with the raw ingredients for star formation, yet they remain eerily dark. How can something so rich in potential gas clouds spanning hundreds of thousands of light-years fail to spark even a single new star? The answer lies in a delicate cosmic balancing act, one that challenges everything we know about how stars are born. Take the Leo ring itself, a vast, wispy structure orbiting two galaxies nearly 35 million light-years away. Its hydrogen gas could forge millions of suns, yet it lingers in silence. The culprit, turbulence. Unlike the calm, dense clouds where stars typically form, the Leo ring's gas is agitated, stirred by gravitational tides from nearby galaxies. Imagine trying to light a candle in a hurricane. The chaotic motion prevents gas from clumping together, scattering potential stellar nurseries before they can take shape. But here's the twist: this turbulence isn't random. Detailed radio telescope observations reveal the gas moves in coherent, swirling streams, as if guided by invisible forces. Some astronomers suspect dark matter filaments, the universe's shadowy scaffolding, might be orchestrating this chaos, their gravitational pull whipping the gas into a frenzy. Then there's the temperature problem. Star formation requires cold, dense gas, but the Leo ring's hydrogen is oddly warm, heated by ultraviolet radiation from distant galaxies. Without cool pockets to collapse, the gas remains diffuse, like a cloud too thin to rain, yet even this explanation isn't perfect. In pockets where the gas should be cooling, like the ring's densest regions, something keeps reheating it. Could hidden black holes or faint, undetected stars be leaking energy into the void, or is there an entirely unknown process at work, one that disrupts star birth in ways our models can't yet predict? The mystery deepens when we compare the Leo ring to other gas-only structures, like the Smith cloud in our own galactic backyard. This high-velocity gas stream, hurtling toward the Milky Way, also shows a puzzling lack of stars despite being dense enough to form them. The difference: the Smith cloud is cooling, its gas beginning to fragment into star-forming clumps. That suggests gas rings aren't permanently sterile. They might just be stuck in a cosmic waiting game, biding time until turbulence fades or external forces shift. What's clear is this: these starless rings are more than failed galaxies. They're cosmic experiments, natural laboratories revealing the precarious conditions needed to ignite starlight. And as we study them, we're forced to confront an uncomfortable truth that even in a universe teeming with potential, the spark of creation isn't guaranteed. Sometimes the cosmos withholds its fire, leaving us to ponder why. Among the countless galaxies strewn across the cosmos, some wear their rings like ghostly whispers, structures so faint they hover on the edge of invisibility. These ultra-diffuse rings sprawl across vast distances, their starlight stretched thin, barely clinging to detection against the black canvas of space. Unlike the bold, luminous hoops of galaxies like Hoag's object, these wispy rings challenge our instruments and our patience, revealing themselves only through painstaking observation. How do such fragile structures endure in a universe where gravitational tides and galactic collisions routinely tear galaxies apart? Consider the case of Malin 1, a galaxy with a ring so diffuse, its stars are spread thinner than in any known spiral. This colossal structure spans over 650,000 light-years, more than 6 times the width of our Milky Way, yet emits less light than many dwarf galaxies. Its stars are scattered so sparsely that if you stood within its ring, the night sky would appear nearly black, with only a few distant pinpricks of light breaking the darkness. The mystery isn't just its size, it's how something so tenuous hasn't been shredded by the gravitational pull of neighboring galaxies or the tidal forces of its own dark matter halo. One clue lies in their origins. Many ultra-diffuse rings may be the remnants of galactic encounters where the collision was gentle, more a grazing touch than a head-on smash. When galaxies interact at just the right angle and speed, they can extrude streams of stars and gas without the violent compression that triggers star formation. The result: a ring of faint, aging stars, drifting lazily through space like smoke from a long-extinguished fire. But fragility isn't their only oddity. Some, like the rings around the galaxy UGC 13812, defy expectations by existing in near-total isolation, far from the gravitational turmoil of galaxy clusters. Without external forces to disturb them, these rings could persist for billions of years, fading slowly like dying embers. Then there's the dark matter factor. In most galaxies, dark matter acts as an invisible scaffold, stabilizing their structure, but in ultra-diffuse rings, this scaffolding might be patchy or incomplete, leaving the stars within it vulnerable. Yet somehow they hold together. Some theorists propose these rings are enshrouded in fluffy, dark matter halos, low-density clouds that cradle the stars without crushing them. Others suggest a more radical idea, that these rings are the visible tracers of dark matter filaments, the cosmic web's hidden threads, with stars clinging to them like dew on a spider's silk. What's certain is that these ghostly rings force us to rethink durability. In a universe where the rule is survival of the densest, ultra-diffuse rings are cosmic exceptions, proof that even the faintest structures can outlast the chaos around them, if only by a whisper. Some ring galaxies don't just glow, they bristle with radial spokes, like skeletal fingers stretching toward the void, and NGC 6028 is the poster child for this cosmic peculiarity, its delicate ring crisscrossed by faint, spindly streaks that defy simple explanation. These aren't the orderly spiral arms of a typical galaxy, they're chaotic, asymmetrical tendrils, as if the ring were cracking under some unseen pressure. What could carve such eerie structures into a galaxy's fabric? The answer may lie in forces both violent and subtle, weaving a tale of magnetism, gravity, and celestial wreckage. Start with magnetism. Galactic magnetic fields, though invisible, shape gas and dust like unseen hands molding clay. In most galaxies, these fields align with rotation, creating smooth, coherent structures. But in spoke-riddled rings like NGC 6028, simulations suggest turbulence from past collisions could have tangled the magnetic lines, turning them into cosmic knitting needles. As charged particles spiral along these twisted fields, they might trace out jagged paths, lighting up as faint spokes in radio telescopes. Supporting this, observations reveal these spokes often glow brightest in polarized light, a telltale sign of magnetic influence. Yet magnetism alone can't explain their persistence. Over time, galactic rotation should shear these features into oblivion unless something, perhaps dark matter, anchors them in place. Then there's the debris theory. When galaxies collide, they don't just merge cleanly, they scatter wreckage of stars, gas, and dust flung outward in chaotic streams. In NGC 6028, these remnants might have settled into unstable orbits, clumping along gravitational troughs like cars on a roller coaster. Over millennia, tidal forces could stretch these clumps into radial streaks, frozen in place by the delicate balance between the galaxy's spin and its halo of dark matter. The most compelling evidence, spokes often appear in pairs or clusters, mirroring the predictable fallout patterns of past collisions. But here's the twist, some spokes aren't static. In UGC 12988, Hubble images captured faint streaks shifting over decades, drifting like shadows across the ring. This suggests they're not just scars, but active structures, perhaps streams of gas condensing into stars or dark matter substructures plowing through the disk like celestial bulldozers. Whatever their origin, one thing is clear, these spoked rings are more than artistic quirks. They're cosmic clocks encoding the timing and violence of ancient impacts, and their very existence challenges our assumptions about how galaxies heal or fail to after catastrophe. Elliptical galaxies are the universe's quiet giants, smooth, featureless blobs of ancient stars, drifting through space like retired sentinels. Unlike their spiral cousins, they're not known for drama. No swirling arms, no glittering disks, and certainly no rings. At least that's what astronomers thought, until they stumbled upon PGC 100714. This cosmic oddity shatters expectations, flaunting not one but two pristine rings nestled inside its elliptical body. It's like finding a whirlpool inside a bowling ball, and its very existence forces us to rewrite the rules of galactic evolution. Rings in elliptical galaxies shouldn't exist. These galaxies are relics of violent mergers, where collisions between spirals erase all traces of delicate structure, leaving behind a chaotic soup of stars. Over time, gravity smooths them into bland, symmetrical orbs. So how did PGC 100714 defy the odds? The answer lies in a cosmic balancing act. Unlike the violent head-on crashes that typically create ellipticals, this galaxy might have formed from a gentler, off-center collision, a sideswipe that left some of the original spiral's gas intact. As the debris settled, the surviving gas could have pooled into a ring, fueled by fresh material siphoned from a passing dwarf galaxy, but the real shocker is the second ring, a faint outer loop that defies even this explanation. Some astronomers speculate it's a relic of a second, more ancient merger, frozen in time like a ghostly echo. Then there's the star formation puzzle. Ellipticals are famously red and dead, their gas exhausted long ago, leaving no fuel for new stars. Yet PGC 714's inner ring blazes with young, blue stars, betraying recent activity. This suggests the galaxy isn't just a passive relic, it's a silent rebel, quietly recycling gas or stealing it from neighbors to keep its rings alive. Telescopes like Hubble have spotted similar oddities, ellipticals with faint, dusty rings or patches of star formation, hinting that PGC 714 isn't entirely alone. But the rarest feature of all, stability, rings and spirals often fade as density waves disperse or collisions disrupt them. In ellipticals, where stars orbit chaotically in all directions, any ring should unravel within millions of years. Yet here they are, persisting for billions. The secret might lie in these galaxies' dark matter halos, whose gravitational grip could be sculpting and stabilizing the rings like invisible hands shaping clay. Or perhaps the stars themselves are the key, their orbits finely tuned to create a standing wave, a cosmic feedback loop that keeps the ring intact. Every new discovery peels back another layer of mystery. PGC 714 isn't just a fluke, it's a clue. If rings can thrive inside galaxies designed to destroy them, what else have we overlooked in the quiet corners of the cosmos? Most galaxies spin like clockwork, orderly, predictable, with stars and gas all moving in the same direction, but NGC 4622 laughs in the face of convention. This spiral galaxy doesn't just have a ring, it has a ring that spins backward, rotating against the flow of the galaxy itself. It's like watching a river suddenly reverse course midstream, defying gravity's usual rules. These counter-rotating rings aren't just rare, they're cosmic paradoxes, and their existence forces us to rethink how galaxies grow and change over time. The mystery begins with their formation. One leading theory points to a galactic robbery, an act of celestial piracy, where NGC 4622 stole gas from a passing neighbor. But here's the catch: the victim galaxy was orbiting in the opposite direction. When this retrograde gas fell into NGC 4622, it didn't align with the galaxy's natural spin. Instead, it retained its backward momentum, settling into a ring that stubbornly rotates the wrong way. Think of it like pouring water into a spinning carousel. If you pour it against the spin, the liquid retains its own motion, swirling in defiance. Over time, this misaligned gas ignites into stars, creating a luminous ring that flips the script on galactic mechanics. But stolen gas isn't the only explanation. Some simulations suggest these backward rings could be scars from a full-blown galactic merger, where a smaller galaxy plunged into its larger host against the spin of the disk. The collision's violence would have twisted the orbits of stars and gas, leaving behind a ring that spins in reverse like a wound that never healed. Supporting this, NGC 4622's outer arms also show signs of distortion, their shapes warped as if still reeling from the impact. Yet even this explanation raises questions. Mergers are chaotic, messy events, so why would the result be a pristine, isolated ring? Some astronomers argue the answer lies in dark matter's subtle influence, its gravitational pull sculpting the debris into a coherent structure over billions of years. The strangest part, these backward rings aren't just curiosities, they're cosmic time capsules. By studying their motion, astronomers can reconstruct the galaxy's violent history like detectives reading fingerprints at a crime scene. In NGC 4622, the counter-rotating ring stars are younger and bluer than those in the main disk, hinting at a relatively recent disruption. But in other galaxies, like ESO 509-G026, the backward spinning material is ancient, suggesting the collision happened so long ago, the galaxy has nearly forgotten it. Then there's the stability problem. Conventional wisdom says counter-rotating rings should tear themselves apart, their opposing motions creating friction that erodes the structure. Yet NGC 4622's ring persists, pristine and unchanging. Some researchers propose magnetic fields might act as cosmic glue, stabilizing the ring by threading through its gas. Others speculate dark matter's invisible hand could be anchoring the ring, its gravity overriding the chaos. Every backward ring tells a different story, but one thing unites them: they're proof that galaxies don't always play by the rules. In a universe where order seems to reign, these cosmic rebels remind us that chaos and beauty can flourish in the most unexpected ways. Galaxies usually settle into a predictable rhythm, stars and gas moving in harmony, like dancers in a well-rehearsed ballet. But ESO 509-98 throws that elegance out the window. This chaotic beauty doesn't have just one ring, it has multiple, each whirling at a different angle, tilting and intersecting like a cosmic game of pickup sticks. Most rings align neatly with their galaxy's disk, but here, the rings seem to defy each other, orbiting in a tangled mess that shouldn't hold together. Yet somehow it does. The secret lies in a history of violence. Unlike the gentle mergers that form orderly rings, ESO 509-98 likely endured a series of brutal collisions, each one dumping fresh material into the mix at odd angles. Picture a snow globe shaken repeatedly. Every impact sends debris swirling in new directions, layering orbits atop one another until the whole system teeters on the edge of collapse. Normally, gravity would smooth these chaotic orbits into a single plane over time, but ESO 509-98's rings persist, suggesting something. Perhaps an unusually lumpy dark matter halo is propping them up, preventing the galaxy from settling into equilibrium. Then there's the question of fuel. Rings form where gas is compressed, but maintaining multiple rings requires a delicate balance. Too much gas and the rings merge, too little and they fade. In ESO 509-98, radio telescopes reveal rivers of hydrogen flowing along the ring's edges, constantly replenishing them like cosmic plumbing. Some of this gas might come from cannibalized dwarf galaxies, their stolen material funneled into unstable orbits. Other streams could be intergalactic gas, pulled in from the void during close encounters with neighboring giants. The most astonishing detail: these rings aren't just misaligned, they're dynamic. In most galaxies, rings rotate smoothly, but here they wobble. Observations show the innermost ring precessing, its axis slowly twisting like a top losing momentum. This hints at unseen forces tugging at the structure, possibly from dense dark matter clumps or the gravitational echoes of past collisions. Meanwhile, the outermost ring appears to tilt farther over time, as if the galaxy itself is slowly capsizing. ESO 509-98 isn't just an oddity, it's a challenge. If rings can survive such chaos, what does that say about our models of galactic evolution? Are we underestimating dark matter's role in stabilizing the impossible? Or is this galaxy a fleeting exception, a cosmic house of cards destined to collapse? Every new observation peels back another layer, revealing a universe far wilder than we ever imagined. Most rings in space appear frozen in time, static hoops of stars and gas that barely change over millions of years, but some have a heartbeat, rhythmically expanding and contracting like cosmic lungs. These pulsing rings aren't just dynamic, they're alive with activity, their movements betraying hidden forces at work. Take the case of NGC 1291, a galaxy where the ring isn't just glowing, it's breathing, oscillating between 50,000 and 150,000 light-years in diameter over epochs. Astronomers first noticed this slow-motion pulse by comparing decades of observations, watching as the ring's outer edge brightened and dimmed in a cycle lasting hundreds of millions of years. The culprit, a dance of violence and rebirth. Unlike rings formed in a single collision, pulsing rings endure recurring trauma, repeated brushes with neighboring galaxies, or the gravitational jostling of unseen dark matter clumps. Each close encounter sends a ripple through the ring, compressing gas clouds and triggering bursts of star formation. As those new stars ignite, their radiation pushes back, expanding the ring outward until gravity inevitably pulls it tight again. It's a feedback loop of creation and resistance, like a symphony where every crescendo is met with an equal and opposite silence. The result is a ring that doesn't just shine, but breathes, its rhythm echoing the cadence of its galactic environment. Then there's the mystery of the missing energy. For a ring to pulse this dramatically, simulations show it should lose momentum over time, like a swinging pendulum slowly coming to rest. Yet NGC 1291's ring shows no sign of fading. Some theorists point to dark matter's invisible hand. Its gravitational nudges might be injecting energy back into the system, keeping the ring's oscillations alive. Others propose a wildcard. Black holes, small, wandering black holes within the ring, could be stirring the gas like spoons in a pot, their occasional mergers releasing gravitational waves that kick-start new pulses. But the most astonishing pulsing rings are the ones without any obvious trigger. In isolated galaxies like UC 4591, where no neighbors are close enough to disturb it, the ring still expands and contracts like clockwork. Here, the pulse might be driven from within, perhaps by the galaxy's own bar, a dense structure of stars at its core that acts like a gravitational paddle, rhythmically pushing and pulling the ring's gas. Or maybe the ring itself is unstable, its delicate balance between rotation and gravity prone to natural oscillations, like a spinning coin wobbling before it falls. Pulsing rings are more than cosmic oddities. They're living records of a galaxy's history. Each expansion encodes a collision, each contraction a moment of rebirth. And as we study their rhythms, we're reminded that even in the vastness of space, nothing ever truly stands still. At the heart of many ring galaxies, something even stranger than the rings themselves lurks in the darkness, a supermassive black hole so powerful, it doesn't just consume light, it casts a shadow. Not a metaphorical shadow, but a real observable void in the fabric of space, etched against the glowing gas of its own accretion disk. These black hole shadows aren't mere absences, they're cosmic silhouettes, revealing the violent ballet of matter spiraling toward oblivion. And in ring galaxies, where structure and chaos collide, these shadows take on forms that defy even our wildest expectations. Take the case of NGC 1097, a ring galaxy where the central black hole's shadow stretches across its dusty nucleus like a stain. Using the Atacama Large Millimeter Array, ALMA astronomers zoomed in on the galaxy's core, expecting the usual blur of hot gas. Instead, they found a crisp, dark circle surrounded by a razor-thin ring of dust, glowing with the heat of a trillion doomed suns. This shadow isn't static. It flickers as clumps of matter plunge into the black hole, warping the surrounding spacetime like ripples in a pond. What makes ring galaxies special is how their unique structure amplifies this phenomenon. The galaxy's outer ring acts like a lens, funneling gas and dust toward the center, where the black hole's gravity shreds it into a swirling maelstrom. The result, a shadow sharper and more pronounced than in most other galaxies, a perfect marriage of galactic architecture and celestial violence. But here's the twist, these shadows aren't just voids, they're maps. By studying their size and shape, astronomers can measure the black hole's spin, a property so extreme, it twists spacetime itself into a vortex. In ring galaxies like Messier 94, the shadows appear slightly elongated, hinting at black holes spinning at nearly the speed of light. That spin, combined with the galaxy's ring-shaped gas flows, creates a feedback loop of destruction. As matter crashes into the black hole, it emits jets of radiation so intense they blow outward like cosmic hurricanes, sculpting the surrounding ring into bizarre, asymmetrical shapes. Then there's the mystery of the missing shadows. Some ring galaxies, like SE2141, host supermassive black holes that could cast visible shadows, yet all my observations show only faint, patchy silhouettes. The leading theory, their dust rings are tilted, obscuring our view of the darkness within. Others might be too ravenous. If a black hole consumes matter too quickly, its accretion disk becomes a turbulent mess, smearing the shadow into invisibility. These shadows are more than just cosmic curiosities. They're windows into the most extreme environments in the universe, where gravity reigns supreme and the laws of physics stretch to their breaking point. And as we peer deeper into their darkness, we're forced to confront a humbling truth that even in the brightest corners of the cosmos, the deepest mysteries often lie in what we cannot see. Most galaxies glow with the familiar light of stars, but some ring galaxies radiate something far stranger: pulses of X-rays, searing infrared, or even gamma rays blazing from their hoops like cosmic lighthouses. These aren't just bright spots, they're anomalies, betraying forces at work that shouldn't exist in such serene structures. Take ARP-147, a ring galaxy where the outer band flickers with X-rays so intense they outshine the core. At first glance, it defies logic. How can a ring, a structure typically made of cold gas and aging stars, emit radiation usually reserved for black holes or supernova remnants? The answer lies in the shadows, where violence and creation collide. Peering into these glowing rings reveals hidden stellar nurseries on overdrive. In ARP-147, collapsing gas clouds birth massive stars at a frenzied pace, their short, violent lives ending in supernova that flood the ring with X-rays. But the real surprise, these nurseries aren't scattered randomly, they're clustered along the ring's inner edge, as if something triggered a synchronized burst of star formation. Astronomers suspect the galaxy's own past holds the key. When a smaller galaxy punched through its center millions of years ago, the shockwave compressed gas into dense knots, igniting chains of supernova explosions that still echo today. Each detonation heats surrounding gas to millions of degrees, making the entire ring shimmer in X-rays like a neon sign in the void. Then there's the infrared enigma of SE7742, a ring so drenched in heat, it glows brighter in invisible light than invisible wavelengths. Here, the culprit isn't stars, it's dust. Thick clouds of cosmic soak up ultraviolet radiation from young stars, re-emitting it as infrared, but the scale is all wrong. The ring's infrared output suggests far more dust than typical models predict, as if the galaxy is cloaked in the ashes of countless dead stars. Some researchers propose a dark twist. The dust might be laced with complex molecules, even organic compounds, forged in the wakes of supernova. If true, these rings could be cosmic factories, churning out the building blocks of life alongside their dazzling light shows. But the most bizarre glow comes from galaxies like MCE+0530, where the ring flickers with gamma rays, the universe's most energetic light. Normally, this signature points to an active galactic nucleus, a supermassive black hole feasting on its surroundings, yet MCE+050330's core is eerily quiet. Instead, the gamma rays emanate from the ring itself, possibly from pulsars spinning neutron stars left behind by supernova, or even dark matter annihilation, where hypothetical particles collide and annihilate in bursts of light. It's a frontier of astrophysics, where every anomalous glow forces us to question what we know about particle physics, star formation, and the hidden engines powering these cosmic oddities. These radiant rings aren't just pretty lights, they're portals into extreme physics. From superheated gas to potential dark matter signals, each wavelength tells a story of forces beyond our everyday experience. And as telescopes like James Webb and Chandra peer deeper, one thing becomes clear: in the universe's quietest corners, the most luminous secrets are waiting to be uncovered. Among the swirling stars and glowing gas of ring galaxies, some of the most intriguing mysteries might not be visible at all: orphaned worlds, drifting alone in the vast gaps between these cosmic hoops. We assume planets form in the cozy embrace of a star system, but what happens when a galactic collision flings them into the void? These rogue planets, untethered from any sun, could be hiding in the darkness of ring galaxy gaps, invisible to conventional telescopes yet silently shaping the structure around them. Imagine a planet the size of Jupiter, ejected from its birthplace during the violent encounter that formed the galaxy's ring. Now it drifts in the cold expanse, its atmosphere freezing into an icy shell as it orbits the galaxy's core in perpetual twilight. Without a star to warm it, the only heat comes from the slow decay of radioactive elements in its core, a faint, dying ember in an endless night. These solitary worlds might be more common than we think. When galaxies collide, the gravitational chaos doesn't just rearrange stars, it can hurl entire planetary systems into the abyss. Some simulations suggest that for every star in a ring galaxy, there could be thousands of these nomad planets, wandering the gaps like ghosts. But how do we find something that emits no light? The answer lies in a cosmic trick called microlensing. When a rogue planet passes in front of a distant star, its gravity bends the starlight like a lens, creating a brief but detectable brightening. Surveys like the optical gravitational lensing experiment, OGLE, have already spotted rogue planets in our own galaxy, but ring galaxies present a unique opportunity. Their dense, well-defined gaps act like cosmic shooting galleries, increasing the chances of a lensing event. If we monitor these gaps long enough, we might catch the telltale flicker of an orphaned world warping the light of a background star. The real surprise: some of these planets might not be entirely dead. Tidal forces from the galaxy's core or interactions with passing stars could heat their interiors, creating subsurface oceans beneath miles of ice. In the darkness of a ring gap, these hidden seas might persist for billions of years, silent, alien abodes where life, against all odds, could still cling. It's a tantalizing thought that the most isolated places in the universe might harbor secrets even stranger than the rings themselves. And then there's the dark matter factor. If these rogue planets cluster in certain regions of the gaps, their combined gravity could subtly warp the ring's structure, creating kinks or asymmetries that betray their presence. Future telescopes like NASA Nancy Grace Roman Space Telescope could map these distortions, turning the gaps of ring galaxies into hunting grounds for the universe's loneliest worlds. Every flicker of light, every unexplained warp, might be a clue, a whisper from a planet that lost its sun but found a home in the dark. Redshift, the stretching of light toward the red end of the spectrum, is supposed to be the universe's most reliable measuring tape. It tells us how fast galaxies are moving away from us, how far they are, even how the cosmos expands. But what happens when a single ring galaxy gives us multiple, conflicting answers? That's the enigma of inconsistent redshift, where one galactic ring shows stars and gas moving at wildly different speeds, defying the laws we thought governed the universe. Take the case of UGC 4518, a ring galaxy where the inner stars race away from us at nearly 2,000 kilometers per second, while the outer ring creeps along at a sluggish 300. According to everything we know, this shouldn't happen. Redshift is tied to motion and distance, so stars bound to the same galaxy should move in sync, like riders on a carousel. Yet here the carousel is tearing itself apart. At first, astronomers assumed a glitch of faulty instruments, obscured dust lanes, or light contaminated by foreground objects. But repeated observations with telescopes like Hubble and the Very Large Telescope in Chile confirmed the mismatch. The numbers don't lie. The ring is, by all accounts, breaking the rules. One radical explanation: dark energy isn't uniform. This mysterious force, thought to drive the universe's accelerated expansion, might vary in strength across space, tugging harder on the inner stars than the outer ones. If true, it would upend cosmology as we know it, suggesting dark energy interacts with matter in ways our models never predicted. Others propose a darker twist, that the outer ring isn't part of the galaxy at all, but a chance alignment with a separate, more distant structure, a cosmic illusion. Yet even this fails to explain why such alignments appear far more often around ring galaxies than any other type. Then there's the strangest possibility of all, that redshift itself isn't the perfect yardstick we believed. Quantum physics hints that light might behave differently in extreme gravitational environments, like those near a ring galaxy's warped core. If photons lose energy climbing out of these twisted regions, their light could appear artificially reddened, skewing our measurements. It's a fringe idea, but one gaining traction as more of these redshift-defying rings emerge in surveys. Every conflicting number is a clue, a whisper that our understanding of the cosmos might be missing a page. And as we stare into these cosmic anomalies, we're forced to ask, are we seeing errors or the first cracks in a much deeper mystery? Most galaxies boast round or oval cores, smooth and unbroken like cosmic eggs. But NGC 1291 breaks the mold. Its heart isn't a sphere, it's a diamond. This dazzling geometric core, sharp-angled and precise, gleams at the center of its ring like a jewel set in celestial silver. How does a universe ruled by gravity and chaos produce something so perfectly angular? The answer lies in the hidden forces shaping galaxies from within, where bars, mergers, and the ghostly hand of dark matter conspire to carve cosmic masterpieces. Start with galactic bars, dense structures of stars slicing through a galaxy's core like the spine of a cosmic fish. In most spirals, these bars are straight, funneling gas inward to feed star formation. But in NGC 1291, something extraordinary happened. Observations suggest the bar buckled, its stars pulled into a boxy or peanut-shaped orbit by gravitational resonances. Over time, as the galaxy rotated, this twisted bar began to shine brightest at its corners, creating the illusion of a diamond when viewed face-on. Supporting this, infrared images reveal the core's true shape, a three-dimensional box that only appears diamond-like from our vantage point. It's a trick of perspective and physics, where stellar orbits align into a geometric marvel. Then there's the merger theory. When galaxies collide, their cores don't always merge neatly. Computer simulations show that off-center impacts can stretch a galaxy's central bulge into strange, asymmetrical shapes, including diamonds. The collision's violence sends stars surging into chaotic orbits, only for gravity to gradually tidy them into sharp-angled configurations. In NGC 1291's case, faint stellar streams winding through its outskirts hint at a long-ago encounter, as if the galaxy hasn't fully forgotten the trauma that sculpted it. But the real surprise, these diamond cores might be cosmic clocks. Their sharp angles are fragile. Over billions of years, gravitational interactions should soften them back into ellipses. The fact that we see them at all suggests they're either younger than we think, or some unseen force like a dark matter subhalo is propping them up. Telescopes like the James Webb Space Telescope are now peering into these geometric enigmas, measuring the motions of their stars to uncover what keeps them so defiantly crisp. What's clear is this: rings with diamond cores aren't just pretty anomalies, they're snapshots of galactic evolution caught mid-transformation, where chaos and order collide to create something utterly unexpected. And as we study them, we're reminded that even in the vastness of space, perfection can emerge from the unlikeliest of places. Some ring galaxies defy the laws of cosmic permanence. They glow brilliantly one moment, then fade into near invisibility the next, as if someone flipped a celestial light switch. The case of NGC 2022 is particularly haunting. Discovered in 1974 with a luminous ring spanning 80,000 light-years, follow-up observations just 2 decades later showed the structure had dimmed by nearly 60%, its once vibrant blue stars now barely a smudge against the blackness of space. Was this a natural cosmic fade-out, or were we witnessing the limits of our own technology? The answer lies somewhere between the mysteries of stellar evolution and the blind spots of human observation. At first glance, fading rings suggest a simple explanation: stars aging out of existence. Massive blue stars, the kind that light up galactic rings, burn bright and fast, some surviving only a few million years before collapsing into supernova or cooling into dim embers. When these short-lived giants die out en masse, the ring's glow dims accordingly, but NGC 2022's rapid disappearance tells a stranger story. Spectral analysis revealed its stars weren't just aging, their light was being absorbed by something. Thick curtains of cosmic dust, likely ejected by the very supernova that ended those stars' lives, now shroud the ring like a funeral veil. This dust wasn't present in early observations, meaning the galaxy essentially cloaked itself in its own ashes, a self-inflicted vanishing act. Then there's the telescope factor. Many disappearing rings, like ARP 148, were first documented by older observatories with limited sensitivity to certain wavelengths. When modern telescopes like Hubble or the James Webb Space Telescope re-examined these systems, they often found the rings weren't gone, just transformed. Infrared reveals structures hidden to optical scopes, showing rings still faintly glowing in heat signatures from cool red dwarfs or dust warmed by hidden black holes. It's a sobering reminder that the universe doesn't change as much as our ability to see it does, but the most unsettling vanishing rings are those like UGC 4591, where neither aging stars nor dust can fully explain the fade. Here, the ring hasn't just dimmed, it's disintegrated, its stars scattered into the void. Simulations point to a possible culprit: dark matter subhalos, invisible clumps of mass passing through the ring like ghosts. Their gravitational nudges could have destabilized stellar orbits, flinging stars outward until the ring dissolved into the galaxy's halo. If true, these vanishings aren't endpoints, but transitions the moment a ring galaxy sheds its defining feature to become something else entirely. Whether cloaked in dust, overlooked by technology, or unraveled by unseen forces, these disappearing rings challenge our assumptions about galactic longevity. They prove that even the most dazzling structures in the cosmos are fleeting, and that sometimes the most profound changes happen not in explosions, but in whispers. Magnetic fields are supposed to be the universe's silent orchestrators, invisible lines threading through galaxies, gently guiding gas and stars into orderly patterns. But in certain ring galaxies, those lines aren't just tangled, they're knotted into chaos, twisting and flipping in ways that make no sense. These aren't just messy magnetic fields, they're rebellious ones, defying every rule about how galactic magnetism should work. And the most baffling part, their disorder might be painting a hidden picture of violence, deception, and cosmic secrets we're only beginning to uncover. Take NGC 6662, a ring galaxy where polarized light observations reveal a magnetic nightmare. Instead of the smooth, spiral-aligned field seen in most galaxies, its field lines resemble a ball of yarn after a cat's been at it, jagged loops crisscrossing the ring at random angles, some even doubling back on themselves. Normally, a galaxy's rotation stretches magnetic fields into neat, coherent shapes over time, but here, something's scrambling them like interference on a radio signal. One explanation points to turbulence, the aftermath of a collision so violent, it stirred the galaxy's gas into a froth, churning the magnetic fields into disarray. It's like dropping a handful of iron filings into a whirlpool. The chaos leaves no room for order to reassert itself, yet turbulence alone can't explain the most bizarre detail. In some regions, the magnetic polarity flips abruptly, creating patches where the field points in the exact opposite direction of its surroundings. This isn't just messy, it's mathematically improbable without an external trigger. The prime suspect, an unseen dwarf galaxy, lurking just beyond detection. As this stealthy companion orbits, simulations show its gravity could warp the ring's gas flows, creating shear forces that twist the magnetic fields like taffy. Over time, these twists snap into sharp reversals, leaving behind a fingerprint of the intruder's passage. It's a cosmic game of hide and seek, where the magnetic chaos is the only clue to a ghostly presence. Then there's the dark matter wildcard. In galaxies like UC 3775, magnetic anomalies cluster in regions where dark matter should be densest, suggesting the invisible stuff might be warping spacetime subtly enough to torque the fields. If true, these tangled magnetic rings could become a new tool for mapping the universe's shadowy architecture using magnetism as a proxy for the unseen. But the real shocker comes from galaxies like ENigmatic 644741, where the magnetic fields aren't just twisted, they're amplified. Radio telescopes detect fields 10 times stronger than expected, concentrated in the ring's star-forming regions. Here, the magnetic chaos might actually be fueling creation. As gas collapses to form stars, the scrambled fields act like cosmic springs, storing energy that gets released in bursts, supercharging star birth. It's a paradox. The same disorder that should stifle structure might be enabling it. These magnetic maelstroms are more than curiosities, they're decoders. Every kink, flip, and knot tells a story of forces we can't see, collisions we missed, and physics we don't yet understand. And as we peer deeper into their chaos, one thing becomes clear: in the magnetic heart of a ring galaxy, even disorder has a design. Most galaxies experience supernova as rare fireworks once every few decades, if we're lucky. But ring galaxies turn that logic upside down. These cosmic hoops don't just host occasional stellar explosions, they're supernova factories, producing them at rates up to 10 times higher than normal galaxies. The reason? A perfect storm of chaos and creation, where ancient collisions transform entire regions into cosmic tinderboxes, just waiting to ignite. Take the Cartwheel Galaxy, where astronomers have cataloged more supernovae in the past 50 years than in most galaxies over centuries. Its ring, forged by a smaller galaxy plowing through its center, is a pressure cooker for star birth. Shockwaves from the collision compressed gas clouds into dense knots, igniting waves of massive stars, the kind destined to die young and bright. These stellar giants burn through their fuel in mere millions of years before collapsing in spectacular Type Roman II supernova, scattering heavy elements like cosmic shrapnel. But the real surprise isn't just the frequency, it's the pattern. Unlike the random distribution seen elsewhere, Cartwheel supernova cluster along the ring's inner edge, tracing the exact regions where collision-triggered star formation peaked. It's as if the galaxy is unwrapping a time capsule, revealing bursts of stellar life and death in perfect sync with its violent past. Then there's the strange case of ARP 148, where supernovae don't just explode, they echo. Infrared observations reveal shells of dust surrounding past explosions, each one glowing faintly as new supernovae heat the debris of their predecessors. This creates a feedback loop. Every explosion enriches the ring with metals, seeding the next generation of stars to form with heavier elements, which in turn burn hotter and die faster. The result? A self-sustaining cycle where supernova beget more supernova, turning the ring into a chain reaction of stellar rebirth and destruction. But the most extreme examples come from galaxies like NGC 7742, where supernova aren't isolated events, they're nearly simultaneous. In 2012, astronomers witnessed 3 supernova detonate within weeks of each other in its ring, a statistical impossibility under normal conditions. The culprit, a phenomenon called triggered star formation, where the shockwave from one supernova compresses nearby gas, sparking the birth of new stars that rapidly evolve and explode in domino-like succession. It's stellar teamwork on a galactic scale, with each explosion setting the stage for the next. What makes these supernova rings truly remarkable isn't just their violence, it's their legacy. Every explosion pollutes the galaxy with elements crucial for life: oxygen, carbon, iron. In a sense, these chaotic rings are cosmic forges, hammering raw hydrogen into the building blocks of planets and people. And as we study them, we're catching glimpses of our own origins, reminded that even the most cataclysmic events in the universe can sow the seeds for something new. Some ring galaxies don't just glow, they flicker with patterns so bizarre, they ignite the wildest speculations. Take NGC 247, where sections of its outer ring dim and brighten in irregular pulses, as if cosmic curtains were being drawn across entire swaths of stars. Could these be signs of advanced civilizations constructing Dyson spheres, hypothetical megastructures designed to harness a star's energy? The idea isn't just sci-fi fantasy, it's a tantalizing possibility that even serious astronomers have considered when confronted with anomalies like Tabby's star. But before we jump to alien conclusions, let's unravel the far stranger truths hidden in these enigmatic light patterns. First, the allure of the megastructure theory. In NGC 247's case, certain segments of the ring show abrupt, localized dimming regions where starlight drops by up to 20% before recovering. If a civilization built a partial Dyson swarm, a network of energy collecting satellites around stars in the ring, their transits could theoretically block light in exactly this irregular way. The ring's structure amplifies the mystery. Its stars are already densely packed, making coordinated dimming even more statistically improbable by natural causes alone. It's the kind of anomaly that makes even skeptics pause, but the universe thrives on deception. When astronomers trained radio telescopes on NGC 247, expecting to detect the waste heat of energy harvesting technology, they found something else entirely: vast clouds of cold, fractal dust. These aren't the smooth, uniform shadows of megastructures, they're clumpy, asymmetrical formations, drifting like cosmic cobwebs through the ring. Detailed spectra reveal the dust is rich in complex carbon compounds, the same molecules found in planetary nebulae and comet tails. The dimming, it turns out, comes from natural occultations, dust clouds passing between stars and Earth, their jagged edges creating the illusion of artificial precision. Then there's the timing problem. True Dyson swarms would dim their host stars predictably, repeating at regular intervals as the structures orbit, and NGC 247's flickering follows no discernible rhythm. Instead, it aligns with the galaxy's chaotic internal dynamics regions where supernova shock waves or colliding gas streams churn up dust in erratic waves. Even more damning, the dimming spans wavelengths uniformly, whereas artificial megastructures would block visible light while allowing infrared to leak through. Here, every wavelength dims in lockstep, a hallmark of mundane dust, not cosmic engineering. Yet the real twist lies in what these false alarms reveal. While NGC 247's flickers aren't evidence of aliens, they do highlight how ring galaxies act as cosmic amplifiers. Their unique geometry, dense, flat, and rich in overlapping sightlines, makes them perfect laboratories for spotting rare phenomena. Unusual dimming in a normal spiral might go unnoticed, but in a ring, even tiny fluctuations stand out like fireworks in a dark room. That's why astronomers keep searching these structures, not just for aliens, but for everything from rogue black holes to exotic dark matter interactions. So while the dream of finding alien megastructures remains just that, a dream, ring galaxies like NGC 247 offer something equally valuable: a reminder that the universe's natural wonders are strange enough to keep us guessing. And sometimes the most thrilling mysteries aren't the ones we solve, but the ones that push us to look deeper. Light echoes are the universe's way of playing back its most violent moments, ghostly ripples of light that linger long after stellar explosions fade. And in certain ring galaxies, these echoes don't just flicker, they paint entire hoops of light across space, revealing histories of destruction we'd otherwise miss. The most famous example isn't in a ring galaxy at all, but its lessons reverberate through them. SN 1987A, the supernova whose shockwave lit up a pre-existing ring of gas like a cosmic neon sign. For decades, astronomers watched as light from the explosion traveled outward, striking the ring and re-radiating outward in an ever-expanding halo. But in ring galaxies, this phenomenon isn't a one-time event, it's a chronicle written in light, where multiple echoes overlap, creating a layered record of violence stretching back millions of years. Take the case of NGC 2623, a ring galaxy where Hubble spotted concentric rings of ultraviolet glow like ripples in a pond, spreading outward from a central point. These weren't new stars, they were light echoes from a supernova that detonated nearly 2 centuries earlier, its energy bouncing off dust lanes in the galaxy's ring. The geometry of ring galaxies makes them perfect echo chambers. Their flat, uniform structures act like celestial projection screens, ensuring light from even modest explosions gets amplified and preserved. In NGC 2623, astronomers realized they weren't seeing one echo, but several, each ring marking where the same blast's light hit different layers of dust at different times. By measuring the spacing between these rings, they could reconstruct the explosion's energy and the 3D structure of the galaxy's hidden dust clouds with unprecedented precision. Then there's the mystery of the delayed echoes. In galaxies like ARP 248, infrared telescopes have detected rings glowing faintly around sites where no supernova have been observed in human history. These are echoes from explosions so ancient, their original light reached Earth long before telescopes existed, but the rings tell another story. Shockwaves from those blasts are still traveling through interstellar gas, heating it enough to emit secondary light millennia later. It's as if the galaxy itself remembers its own cataclysms, whispering their secrets to anyone patient enough to listen, but the most astonishing echoes are the ones that defy explanation. In UTC 4591, a peculiar ring galaxy near the edge of the observable universe, astronomers found a series of perfectly circular X-ray rings, far too symmetrical to be natural remnants. The leading theory, a supernova's shockwave collided with a previously unknown shell of gas, possibly ejected by the progenitor star centuries before its death. The collision sculpted the gas into a temporary sphere, which the echo then illuminated like a lantern. These structures shouldn't last as gas disperses, shockwaves fade, yet there they were, pristine as a photograph. Some researchers now think magnetic fields might be stabilizing them, turning what should be fleeting phenomena into cosmic monuments. These echoing rings are more than just pretty light shows. They're forensic tools letting us rewind cosmic violence frame by frame, and as we decode their flickering messages, we're glimpsing a universe where nothing ever truly disappears, where even the briefest explosion leaves a signature that lingers, waiting to be read. When galaxies collide, they don't always leave behind neat, symmetrical rings. Sometimes they fling stars into sprawling, ribbon-like arcs that stretch hundreds of thousands of light years into the void. These tidal tales are the scars of cosmic violence, the lingering aftermath of galaxies tearing each other apart, and when they appear alongside rings, they create some of the most chaotic and breathtaking structures in the universe. Consider ARP 248, a ring galaxy with twin tidal tails spiraling outward like the arms of a celestial whirlpool. Unlike the orderly rings of Hoag's object, this galaxy looks like a wreck, stars scattered in long, shimmering streams, the remnants of a smaller galaxy shredded by gravitational forces. These tails aren't just debris, they're time capsules. By tracing the motions of stars within them, astronomers can reconstruct the collision that birthed the ring, like detectives piecing together a crime scene. The brightest stars in the tails are often blue supergiants, short-lived beacons that tell us the collision happened relatively recently, on cosmic timescales. Farther out, the older, redder stars hint at earlier disruptions, painting a layered history of violence. Then there's the eerie similarity to the antennae galaxies, a pair of spirals locked in a messy merger. Like ARP-248, the antennae have flung off colossal tidal tails, but with a key difference: they haven't yet formed a central ring. This suggests ring galaxies might be a later stage of galactic evolution, where the chaos of collision settles into a temporary symmetry before the tails fade into the darkness. Yet some rings, like those in UGC 9618, keep their tidal tails for billions of years, their stellar streams stubbornly resisting dispersal. Why the answer might lie in dark matter. Simulations show that galaxies with dense, asymmetric dark matter halos can trap tidal debris in stable orbits, preserving these structures long after they should have dissolved. The real puzzle comes from galaxies like NGC 7727, where the tidal tails aren't just trailing behind, they're actively forming stars. Dense knots of gas within these streams collapse under their own gravity, igniting blue-white clusters that glow like pearls on a cosmic string. It's a paradox, destruction giving birth to creation. And in the deepest reaches of these tails, astronomers have even spotted orphaned globular clusters, ancient, tightly packed groups of stars ripped from their host galaxies and left to wander the void alone. These tidal tail rings are more than just beautiful accidents. They're proof that chaos can leave behind its own kind of order, and that even in the wreckage of galactic collisions, the universe finds ways to build something new. Galaxies aren't supposed to come back from the dead, especially not their rings. Once a luminous hoop of stars fades into the darkness of space, we expect it to stay gone, swallowed by time and gravity. Yet the cosmos loves breaking its own rules. In a handful of galaxies, rings don't just vanish, they resurrect, flaring back to life like phoenixes rising from cosmic ashes. These aren't random bursts of star formation, they're evidence of galactic cycles so precise, they border on celestial clockwork. Take NGC 2944, a galaxy where astronomers watched in disbelief as a dim, ancient ring suddenly blazed with newborn stars. Decades of observations showed the ring had faded nearly to invisibility, its blue giants long dead, leaving only the faint red glow of aging dwarfs. Then almost overnight it lit up again, not in patches but in a synchronized wave sweeping around the entire structure. The explanation: a delayed starburst, triggered by gas that took millions of years to cool and collapse after a collision. When galaxies merge, shockwaves compress gas, but the actual ignition of stars can lag behind, waiting until conditions are just right. In NGC 2944's case, the delayed fireworks were so intense, they briefly outshone the galaxy's core. But the real marvels are galaxies like UGC 4591, where rings don't just reignite once, they pulse like a heartbeat. Here, the cycle repeats every few 100 million years. Gas accumulates in the ring until it reaches a critical density, sparking a firestorm of star birth. Those young stars live fast, die young, and spew their remains back into the void, enriching the gas with heavy elements. Over eons, turbulence settles, and the process begins anew. It's a self-sustaining loop, where each generation of stars plants the seeds for the next. Telescopes have even caught these galaxies mid-cycle, with half the ring ablaze in blue light and the other half dark, as if paused between breaths. Then there's the dark horse of resurrection, slingshot gas. In galaxies like ARP-148, simulations reveal a sneaky culprit: gas flung outward during a collision, only to fall back billions of years later like a boomerang. This returning material crashes into the galaxy's outskirts, compressing any lingering hydrogen and reigniting star formation in a ghostly echo of the original ring. The delay between the initial impact and the ring's rebirth can be so long, the two events seem unrelated. Without detailed orbital reconstructions, we'd never connect them. What's truly humbling is how these resurrected rings force us to rethink time itself. On human scales, galaxies appear static, frozen in a single moment. But in reality, they're dynamic ecosystems where destruction and rebirth play out on timelines we're only beginning to decipher. Every revived ring is a reminder: In the grand tapestry of the cosmos, even endings can be beginnings in disguise. Galaxies paint the cosmos in predictable palettes: red cores of aging stars, blue arms of newborn suns, but some ring galaxies scoff at this celestial color theory, flaunting hues so bizarre they rewrite the rules of astrophysics. Take UTC 4591, where the ring burns fiery orange while the core gleams an impossible sapphire. This isn't just an optical illusion, it's a cosmic rebellion, where chemistry, physics, and sheer chaos collide to create colors that shouldn't exist. The first clue lies in metallicity, the abundance of elements heavier than hydrogen and helium. Normally, galaxy cores are metal-rich, forged by eons of supernova, while outer rings remain pristine and blue. But in UTC 4591, spectroscopy reveals the opposite. The ring is laced with iron and carbon, while the core is strangely metal-poor, as if someone scrubbed it clean. How? The answer might involve a galactic heist. When a gas-rich dwarf galaxy collides with a larger one, its metal-poor gas can funnel straight to the center, diluting the core's chemistry while leaving the ring enriched with debris from the collision. It's like pouring fresh water into a murky pond. The center clears, while the edges grow darker. Then there's the wild card of AGN contamination. Active galactic nuclei, supermassive black holes belching radiation, can tint their surroundings in unnatural ways. In NGC 7742, X-ray observations reveal a core so saturated with high-energy particles, it fluoresces electric blue, while the ring glows crimson from cooler, star-forming regions. This isn't starlight, it's black hole pollution, a radiant smear of ionized gas that distorts the galaxy's true colors. The effect is so potent, early astronomers mistook it for evidence of alien megastructures until telescopes like Chandra decoded the radiation's telltale signature. But the ultimate chromatic oddity might be AN 644741, where the ring isn't one color, but a swirling gradient from ultraviolet to infrared. Here, the culprit isn't just stars or black holes, it's dust. Unlike the uniform clouds of most galaxies, this ring's dust is fractal, with textures so fine, they scatter blue light like Earth's atmosphere while letting red light pass unscathed. The result, a ring that shifts color depending on the angle, like a cosmic mood ring. These impossible colors aren't just cosmetic quirks, they're cryptic messages revealing hidden histories of violence, theft, and celestial alchemy. And as we decode their spectra, we're learning that the universe's palette is far stranger and more beautiful than we ever imagined. One of the most peculiar tricks of cosmic perspective occurs when ring galaxies, structures millions of light-years across, mimic objects small enough to fit inside a single star system. At first glance, the resemblance between these galactic hoops and planetary nebulae or protoplanetary disks seems uncanny. The Helix Nebula, for instance, with its glowing ring of expelled stellar material, could be mistaken for a miniature version of Hoag's object when viewed from afar. Both feature luminous rings surrounding a central point, their symmetry so flawless it borders on art, but peel back the layers, and the differences become as vast as the scales separating them. Planetary nebulae form when dying stars shed their outer layers, leaving behind intricate rings of ionized gas no wider than our solar system. These delicate structures last mere tens of thousands of years before dispersing into the void. Ring galaxies, by contrast, are born from cataclysms on an unimaginably grander scale, galactic collisions that send shockwaves through billions of stars, sculpting rings that persist for hundreds of millions of years. The mechanisms couldn't be more different. One is a stellar last breath, the other a galactic rebirth, yet the similarities aren't entirely coincidental. Both phenomena rely on the same underlying physics, the conservation of angular momentum. When a star like the Sun nears death, its spinning outer layers flatten into a disk before being ejected as a ring. When galaxies collide, tidal forces strip gas and stars from their disks, funneling them into similar circular orbits. The results, though separated by scale, mirror each other in form. Even the colors align. The blue hue of young stars in a galactic ring mirrors the oxygen-rich glow of a planetary nebula, while the golden cores of ring galaxies echo the dimming embers of central white dwarfs. The kinship extends to protoplanetary disks, those swirling cradles of dust and gas where planets form. Seen edge-on, systems like HL Tauri reveal dark dust lanes splitting their disks into rings, resembling a galactic ring's cross-section. Again, the scales diverge wildly. Protoplanetary disks span mere astronomical units, while galactic rings stretch for kiloparsecs, but the underlying dance of gravity and spin remains eerily parallel. Even the gaps in these disks, carved by nascent planets, find their galactic counterpart in the star poor voids between a ring galaxy's core and outer rim. What makes this mimicry truly fascinating isn't just the visual echo, it's the way these structures reveal universal patterns. From the smallest stellar nurseries to the largest galactic collisions, the universe returns again and again to the same elegant solutions: rings, disks, and spirals. Each time the context changes, but the signature of angular momentum, turbulence, and gravity's patient sculpting remains. For astronomers, these parallels offer a powerful tool. Lessons learned from studying planetary nebulae can shed light on galactic rings, and vice versa. It's a reminder that the cosmos, for all its immensity, often speaks in repeating whispers. Hidden within the swirling bands of certain ring galaxies lies a relic of the cosmos' infancy: pristine pockets of gas, untouched by the furnaces of star formation, preserving chemical fingerprints from the dawn of time. Unlike the metal-rich clouds of mature galaxies, these molecular time capsules harbor elements in their primordial state, offering a rare window into the universe's chemical adolescence. The Atacama Large Millimeter Array ALMA has pinpointed these anomalies in galaxies like Espedio 418-47, where entire swaths of a ring's gas show no trace of heavy elements, as if frozen in the first billion years after the Big Bang. How does gas remain unprocessed for over 13 billion years? The answer lies in a cosmic quarantine. When ring galaxies form through gentle, off-center collisions, some outer gas gets flung into stable orbits far from the turbulent core, shielded from the supernova and stellar winds that pollute interstellar clouds with metals. In these isolated reservoirs, hydrogen and helium persist alongside trace molecules like hydrogen deuteride and helium hydride compounds so fragile, they're destroyed by even the faintest radiation. ALMA detection of these molecules in the ring galaxy NGC 430 was akin to finding a vial of uncorked perfume from antiquity, its scent miraculously intact. The real surprise comes when comparing these pristine clouds to simulations of the early universe. Their chemistry matches theoretical predictions of cold accretion, a process where virgin gas flows into galaxies along cosmic filaments without heating up. This challenges the long-held assumption that all galactic gas undergoes violent mixing. Instead, ring galaxies may act as cosmic refrigerators, preserving pockets of the universe's original ingredients like celestial amber. Even more tantalizing, some of these clouds show deuterium to hydrogen ratios 100 times higher than the Milky Way's, a smoking gun for gas that's never cycled through stars, where deuterium, normally burned in stellar cores, remains abundant. Yet the most profound implication isn't just about chemistry, it's about origins. By studying these frozen gas rings, astronomers are decoding the conditions that birthed the first stars. Unlike metal-enriched clouds which fragment easily into suns, pristine gas requires far greater densities to collapse, likely forming massive, short-lived stars that shaped the early cosmos. Ring galaxies, then, aren't just relics, they're time machines offering a glimpse into the universe's most transformative era, one molecular whisper at a time. Gravity's grip on galaxies is supposed to be unbreakable. Stars and gas orbiting at speeds precisely dictated by the visible mass tugging at them. But some ring galaxies spit in the face of this cosmic rulebook, their outer rings whirling so fast they should have torn themselves apart eons ago. These aren't just anomalies, they're full-blown rebellions against our understanding of physics, forcing astronomers to confront an uncomfortable truth: either we're missing something fundamental, or gravity itself works differently out there. Take UC 12591, a modest ring galaxy where the outer stars orbit at nearly 300 kilometers per second faster than the Milky Way's suns, despite having only a fraction of the mass. According to Newton's laws, that ring should have flown off into space long ago, like a merry-go-round spinning so fast it flings riders into the grass. Yet there it is, defiantly intact, the simplest explanation: hidden mass. Dark matter could be lurking in unseen clumps, its extra gravitational glue holding the ring together. But here's the catch: detailed gravitational lensing studies show no trace of the dense dark matter halo you'd expect. It's as if the galaxy's gravity has been cranked up by invisible dials we can't locate. This is where modified gravity theories like modified Newtonian dynamics enter the fray. Min suggests that on galactic scales, gravity doesn't weaken as sharply as Newton or Einstein predicted. Instead, it tapers off gently, providing just enough extra pull to explain rapid orbits without invoking dark matter. In ring galaxies where mass is concentrated in thin, luminous hoops, Min tweaks could neatly account for their stubborn cohesion. But Min isn't perfect. It struggles with galaxy clusters and cosmic microwave background data, leaving many astronomers skeptical. Then there's the wild card: tidal debris. Some simulations suggest these hyper-fast rings might be illusions, not stable structures, but transient streams of stars flung outward during collisions, still carrying the momentum of the impact. Like a lasso swung and released, they appear to orbit impossibly fast, but only because we're catching them mid-flight. This could explain fleeting examples like NGC 7742, where the outer ring stars show wildly divergent velocities, hinting at a recent, messy encounter. Yet the most tantalizing cases are those like ARP 147, where the ring's speed stays suspiciously constant across billions of years, far too long for a tidal fluke. Here, the truth might lie in a combination of factors: dark matter arranged in unconventional geometries, unseen black holes anchoring the ring, or even exotic physics like scalar tensor gravity, where the strength of gravity varies with environment. What's clear is this: every gravity-defying ring is a challenge thrown at our models, daring us to think beyond the known. Whether the answer lies in the shadows of dark matter, the fine print of gravity's laws, or something entirely uncharted, these cosmic speedsters remind us that the universe still holds cards it hasn't shown. And as we race to decode their secrets, we're not just solving a puzzle, we're rewriting the rules of the game. Amid the velvet darkness of space, one ring galaxy burns brighter than the rest in UC 1672, a celestial structure so ferociously active, astronomers have dubbed it the Ring of Fire. Unlike the serene blue hoops of galaxies like Hoag's object, this cosmic inferno rages with star formation so intense, its infrared glow outshines entire galaxies 10 times its size. Imagine a cosmic hurricane where every droplet is a newborn star, and you're beginning to grasp the fury of this extraordinary place. What makes this ring so lethal? Density. While typical galactic rings host sporadic stellar nurseries, NGC 1672's ring crams thousands of star-forming regions into a space no wider than our Milky Way's spiral arms. Radio telescopes reveal gas clouds packed so tightly, they collapse under their own weight at breakneck speeds, birthing stars 100 times faster than in our galactic neighborhood. The result is a chain reaction of creation and destruction, supernova detonating every few decades, their shockwaves compressing nearby gas into yet more stars, feeding a self-sustaining cycle of violence. But the real shock comes from the ring's temperature. Most star-forming regions hover around a chilly -200 degrees Celsius, but ALMA spectral scans show patches in NGC 1672's ring blazing at over 50 degrees Celsius hotter than a summer day on Earth. This isn't just star formation, it's star formation cranked to a setting the universe rarely uses, the culprit, a phenomenon called radiation trapping, where the sheer density of young stars saturates the region with so much ultraviolet light, gas can't cool normally. Instead, it stews in its own energy, reaching temperatures that should stifle star birth yet somehow accelerating it instead. The galaxy's core adds another layer of madness. While most ring galaxies feature calm, aging nuclei, NGC 1672's heart is a supermassive black hole on overdrive, spewing jets of plasma that punch straight through the ring. These jets don't suppress star formation, they supercharge it, like blowing on a bonfire. Where the jets collide with the ring's gas, they carve out cavities lined with shock waves, compressing the surrounding material into hyper-dense shells that collapse into superstar clusters. It's a galactic-scale Rube Goldberg machine, where black hole activity begets more stars, which beget more supernova, which feed the black hole in a loop of escalating frenzy. Yet the most haunting detail is the ring's lifespan. Such extreme star formation should burn through its gas in a mere 100 million years, a blink in cosmic time. Instead, studies suggest the ring's been ablaze for at least 1 billion. The secret, a cosmic conveyor belt. Observations reveal filaments of gas streaming in from intergalactic space, replenishing the ring as fast as it consumes its fuel. It's as if the galaxy has tapped into some unseen reservoir, a hidden pipeline funneling fresh kindling into the fire, and NGC 1672 isn't just a curiosity, it's a glimpse into the universe's most extreme environments. A place where the rules of star formation twist into strange new shapes, and where the line between creation and destruction blurs into a single, radiant ring of fire. From ghostly starless rings to diamond-shaped cores, warped magnetic fields to resurrected hoops of light, these 30 phenomena reveal ring galaxies as cosmic laboratories where the universe tests its wildest ideas. Each anomaly we've explored: hyperfast orbits defying gravity, X-ray echoes flickering like cosmic Morse code, even the possibility of rogue planets drifting in the gaps challenges a fundamental assumption about how galaxies live and evolve. These aren't just quirks, they're clues pointing toward gaps in our understanding of dark matter, the nature of gravity, and the very life cycle of galaxies themselves. Consider what these rings have taught us. Double ring structures like Hoag's object prove that galactic collisions can create near mathematical perfection, while galaxies like NGC 2944 show dark matter doesn't always behave as predicted. It clumps, it twists, it lingers where it shouldn't. The Cartwheel Galaxy's supernova factories reveal how violence births creation, and ultra-diffuse rings like Malin, one whisper that even the faintest structures can outlast the cosmos chaos. Then there are the optical illusions, rings mimicking planetary nebulae, light echoes replaying ancient explosions, and colors so bizarre they rewrite the rules of chemistry. Every one of these phenomena is a thread in a larger tapestry, woven from questions we're still learning to ask, but the greatest lesson these galaxies offer isn't just about astrophysics, it's about curiosity. Each time astronomers think they've pinned down the rules, the universe tosses another riddle into the mix. Why do some rings pulse like living things while others vanish without a trace? How can a black hole's shadow sharpen a ring's structure instead of erasing it? And what secrets might still hide in those pristine gas clouds, untouched since the dawn of time? The beauty of these mysteries is that they're not dead ends, they're doorways. For those hungry to explore further, the cosmos never runs out of puzzles. Perhaps you'd like to dive into the enigma of rogue black holes, wander the filaments of the cosmic web, or unravel the paradox of galaxies that existed too early in the universe's timeline. Whatever path you choose, remember this: the night sky isn't just a scattering of stars, it's a conversation, one where every anomaly, every defiance of expectation, is the universe nudging us to look deeper? So keep questioning, keep wondering, because out there, in the silent dance of ring galaxies and beyond, the next great cosmic revelation is waiting.